Our last speaker of this session is Hernán González Leiva from Universidad Adolfo Ibáñez. Hernán, there you go. Thank you very much. So Hernán will give a talk on celestial amplitudes and infrared divergences.
Okay, give me just 1 second to put the presentation mode. Which one is it?
So as usual, I will let you know after 10 minutes once you start, Hernán. Okay.
Okay. I just don't remember exactly where the mode is.
Ahí más abajo, modo pantalla completa. Yes.
Thanks a lot. Okay. Thank you to the organizer for inviting me to give this talk. Today I'm going to describe a very interesting and intriguing relation between scattering amplitudes for massless particles and 2D conformal field theories. I will also try to briefly discuss the role of infrared divergences in this business. This is a working collaboration with Andrea Puma and Francisco Rojas. So, finding a flat space-time holography, like in the same way as ADS-CFT, has been one of my main motivations. And the way I try to approach to it, it's through symmetries. So understanding the symmetries, I would like to construct the putative dual field theory in flat space. So, okay. So on the left-hand side, you have a Penrose diagram of flat space, or from Minkowski space. In fact, like any asymptotically flat space shares the same. See?
Apparently, the full screen mode didn't work because we still see your title slide.
Ah, okay. Let me see. Let me see how I can fix that. Okay.
It is not working.
Yeah,
Control L, quizá.
Yeah, exactly. Just 1 second. 1 second. And now, does it work?
Yeah.
Yeah, perfect. So you can see now.
Yes.
Now you can see.
Perfect.
Yes.
Okay. So what I was saying is that my approach to flat space holography is by studying symmetries. And in the case of gravity mainly, well, on the left-hand side, you have the Penrose diagram of Minkowski space. But in fact, any asymptotically flat space shares the same diagram. Okay. So understanding gravity and imposing boundary conditions on this specific boundary that is called null infinity, because it's where light goes or where lights come from, you can realize that there is a set of symmetries that leave invariant the gravitational field at large distance, and this group is much bigger than Poincaré. In fact, it's infinitely extended by super translations that are time translations that depend on the angles, and also recently, well, almost in 2009, was found that the Lorentz part of the Poincaré group can also be extended to the full conformal group. So the question is here is like, what are the role of the symmetries at the quantum level? So I would like to understand how these symmetries constrain in some way the quantum holographic theory. And to do that, I'm focusing on the S matrix for massless particles because they have a nice interpretation, in the sense that when you study scattering processes in flat space, you basically you have to compute Feynman diagrams, like where states depart in the far past and then they go to the far future. And then you compute this observable, and this observable nicely fit on where you can put all the external states, you can put them in a sphere, okay? So I would like to find, this is what I'm going to show, it's like a correspondence between scattering processes in the bulk and a relation with a conformal field theory on this sphere that is related with, is the sum of the scribe minus and the scribe plus, that from now on I will call it the celestial sphere. So I would like to understand the properties of this 2D theory, if there is such a thing. Okay, so the outlet of my talk is like, to do that, I will do a change of basis. Then I will continue understanding in more detail the scattering of two massless particles. I will give a brief explanation about what happened of divergent infrared gluon amplitudes. It's important because if I want to promote the amplitude to an observable that give me information about the holographic description of the space-time, I need to understand how the infrared divergences fit in that perspective, and I will end up giving some conclusions. So the celestial sphere, loosely speaking, is just the home for massless states, but you are more familiar with it when you see the sky at night. So it's made by at a fixed time. It's all the right light that come to you when you are observing the sky. So are the stars that are very, very far away from Earth. Okay, and since we are interested in relativistic field theories, it's important to know what happened with this symmetry when we look at it from the point of view of the celestial sphere. So when two observers take pictures of the sky at night, let's say one observer is on Earth at rest and the other one is moving at the speed of light, right, at certain speed with respect to him. So we will see that they will not take the same picture. In fact, the points on the celestial sphere, these points are basically angles. Here I just wrote information in terms of a complex number that is related to two angles, to the spherical coordinate angles. So if I take two pictures, these pictures will be related when R goes to infinity with a map that is a SL2C map. Yeah. So this is a representation of the Lorentz transformations in terms of 2x2 complex matrix with determinant equal to 1. And at the same time, this Lorentz symmetry is the global conformal group in 2 dimensions. So I will try to understand better this description in terms, this symmetry in terms of other kinds of fields. So for that, I will use something called Mellin transform. So in general, when we are studying scattering amplitudes, we are used to using plane wave as the external particles. So they are characterized by omega. Well, in principle here, I have a null vector because a null vector with 2 independent parameters characterize completely a null vector in 2 dimensions. So this quantity, one is the energy and the other one is the position on this celestial sphere. And instead of using plane waves, I will be using this kind of state that is an integration over the energies, where omega no longer appear, and then you sum over all energy states, and also you exchange the energy W by the scaling dimension delta. So this kind of states have very nice properties. The first one is that under SL2C, the Lorentz symmetry or the global conformal symmetry in 2 dimensions transform in this way. And here you can recognize the transformation law of a primary field. in 2 dimensions, a conformal primary. Okay, so this new basis of states transform exactly the same way as the one that appear in conformal field theory. The difference here is that you know that plane waves are normalizable states, so if you want to do the same for these states, they require that delta to have imaginary part, real part equal 1. Yeah, they are not real anymore. They have this form. So this signals the fact that this kind of CFT, the one we are constructing now, is of a different kind, in the sense that, for instance, we are more used to highest weight representations where delta must be positive. Here, it's another kind of CFT where delta is a complex number. Okay, so how do I construct celestial amplitudes? So I start with normal amplitudes, and then for each external leg, I apply a Mellin transform of this type. So here I'm considering n particles, and yeah, so n particles, each one of them with scaling dimension delta k and helicity lk. I will describe it in a more detail in the 4-point case. So the interesting part is that this sort of amplitude is anti-Wilsonian, in the sense that A tilde involves arbitrarily high energy particles. So I need to integrate over all scales, and I cannot restrict to one set of scales. So in that sense, it's a different kind of quantum field theory. Sorry,
you have 10 minutes.
10 minutes?
5 more.
Okay, perfect. So how do I construct the 4-point amplitudes? Well, you can generally they are described by this. They have this form. S and P are the Mandelstam variables. In the case of 4 particles, the scattering lies on a plane. So these have important consequences later. And another important quantity is this conformal invariant ratio that is also related to the scattering angle in the center of mass frame. Okay, so sorry, just to say this, like these numbers L are integers, and for photon and gluons is ±1, and for graviton is ±2. Okay, let me well, this is the generic form of a correlation function in a 2D CFT. You can perform the Mellin integral, and then you get this expression where the product it comes from the fact that you have an SL2C symmetry, and also you have a prefactor. This prefactor encodes, let's say, the dynamical information, because it's the integral over this function B that controls the energy. Also, this function F imposes that there is a delta of R minus R bar that says that scattering lies on a circle. Okay, those are the main features of the 4-point amplitude. Some examples, in the case when B is a constant meaning that doesn't depend on energy, you get F proportional to delta of R minus R bar, and a new delta that tells me that the sum of all the scaling dimensions is equal to 4. And those are examples that appear in gluon amplitudes and in massless QED. Quantum field theories with massless particles. So those cases are scale invariant, and this is the reason why this delta of delta minus 4 appears. But at loop level, there are problems, of course. UV and IR divergences appear. The UV problem is partly understood, and you can think of it like, for instance, in the case of gravitons, you know that the function B goes like the energy square, so the Mellin integral diverges quadratically. This behavior is often in string theory, so we need a UV completion in that case to make sense of this celestial amplitudes. And what you get is that this exponential that appears only in strings gives rise to a well-defined Mellin integral at the end of the day. So the UV problem is more or less understood. Let me just focus on the IR divergences. And for that, I will choose a very specific example where UV divergences are not there. So I choose to study n equals 4 super mills. This is a UV finite theory. However, it has infrared divergences. So here epsilon is 4 minus 2, 4 minus d. Well, d is 4 minus 2 epsilon. And also this expressions also diverges in the IR. So let me just say that, well, one can consider the planar contribution. So when n goes to the SUN gauge group, where n goes to infinity, and you consider the Duff limit, where a is fixed. So then in that case, you can sum over all loop contributions, and you get an exponential factor times a hard piece that you can complete exactly. That depends on R and the coupling A. So the question here, and what we wanted to understand, is that the infrared safe part of this amplitude is preserved under Mellin transform, and the answer is yes, it can be done. And I think I'm over the time, so I will go very fast. You can do such a factorization. You can factorize the n equals 4 planar 4-point amplitudes into two pieces. One is the infrared divergence, and the other one is the hard piece, Mellin hard piece, where the function f that encodes the dynamical information can be computed. A tilde divergent is a regulator dependent operator. It can be written in terms of 4-point correlators, which shows that these infrared divergences, even though they are not well defined, they are universal. So they can be written in terms of CFT 4-point correlators. And well, I want to say that this is not the end of the story. You can do it for other field theories, scalar QED, graviton, where you sum internal virtual gravitons, and this factorization is also possible. So just to conclude, celestial amplitudes reveal a 2D CFT properties of scattering for massless particles. In the case of two particles colliding, this scattering, or the information of the scattering, is encoded in this function f. And for planar n equals 4 sub mills, celestial amplitude is split into hard and infrared pieces as well. So thank you. Sorry, I went over the time. I cannot hear you, Mauro.
Yeah, I always forget to unmute myself. Thank you very much, Hernán, for your talk. Are there any questions?
I went too far.
Francisco, I was expecting yours.
Thanks, Hernán, for the nice talk. Just a very also naive question. So do you expect another example where do you experience such a splitting or not? I mean,
do you expect what? Sorry,
I mean the splitting of this celestial amplitude.
Well, even though the amplitudes are divergent, I would at least expect to factorize the information I can really observe in the colliders from the information that is related to the regulator, let's say. So even though I cannot get rid of it, this factorization still tells me that the information in some way is preserved on the celestial sphere. Is that what you're asking?
Well, no, I just thinking. I mean, There is something that sounds to me related with resurgences, but this is no. I mean, I have not something like important comment to say. I just that
Could
I
be.
have some. I don't know, but I have some ideas, but that's fine. That's fine. Thanks, Hernán.
Okay, good.
More questions?
Because of resummation, right, Francisco?
Sorry, Danilo?
Because of resummation, you say.
Yes.
I have a naive question regarding your dimensional regularization. Maybe I am confused, but usually to regulate infrared divergences, you put d equals 4 plus 2 epsilon, and for UV ones is that we usually choose 4 minus 2 epsilon.
Well, this is not something that I did. It was already done. And in general, with dimensional regularization, you cannot tell if the divergence is UV or IR. You just get like something divergent, and you renormalize the UV part, but then you just get with the IR piece, let's say. So I'm not familiar with this scheme you are telling me that you consider 4 plus 2 epsilon.
Oh, in usual QFT, when you do dimensional regularization, one can do regulate UV and IR divergences.
Yeah, that's true. Yeah, you're
but
right.
you have to remove the poles differently, and therefore for one you choose typically 4 minus 2 epsilon for the UV ones, and 4 plus 2 epsilons for the infrared ones.
Okay.
But maybe here is different. So I don't know if it applies.
Maybe you can do the same. Yeah, but I'm not familiar with what you're telling me. But I can try to look for it, and maybe can give you a more precise answer regarding to it.
Okay, thank you. More questions or comments? No, so if not, we thank Hernán. And with that, we would be closing this first afternoon session of today.